the theme of the 10th lecture, Ampere's law, magnetic field of a solenoid. From this lecture, you will learn the content and significance of Ampere's law, how to calculate the magnetic field of a current-carrying solenoid, and how to find the work done by a magnetic field. And today we have the following vocabulary for our lecture. Sign rule for currents, правила знаков для электрических токов. Magnetic flux, магнитный поток. Magnetic dipole moment, магнитный дипольный момент. Torque, вращающий момент. Ampere's law. Calculations of the magnetic field due to a current have involved finding the infinitesimal field dB due to a current element and then summing all these dBs to find the total field. This approach is directly analogous to electric field calculations. For the electric field problem, we found that in situations with a highly symmetric charge distribution, it was often easier to use Gauss' law to find the electric field. So there is likewise a law that allows us to more easily find the magnetic fields caused by highly symmetric current distributions, and this law is called Ampere's law. It is rather different in character from Gauss' law. Ampere's law is formulated not in terms of magnetic flux, but rather in terms of the line integral of magnetic field around a closed path. It is denoted by this expression. So this is the integral for a closed path, one whose beginning and end points are the same. To evaluate this integral, we divide the path into infinitesimal segments dl, calculate the scalar product of the magnetic field and this element of the path for each segment, and then sum these products, so which is shown in the figure 1. So here we have the current, that is the current carrying conductor, and this is so we know that the magnetic field is produced around this current carrying conductor, and we take any path which encloses this current carrying conductor, any closed path, and we divide these paths around a current carrying conductor into segments with the length dl. We take the scalar product of the magnetic field at this point and the length of the element dl, the segment of the path with length dl. So, and this scalar product gives us the parallel component of the magnetic field. In general, magnetic field varies from point to point, and we must use the value of the magnetic field at the location of each dl, of each segment of length dl. An alternative notation is for this component is this closed line integral over a closed path, where B parallel is the component of the magnetic field parallel to the path element dl at each point. The line integral thus independent of the radius of the circle and is equal to the magnetic constant multiplied by the current passing through the area bounded by this circle. This result doesn't depend on the shape of the path or on the position of the y inside it. If the integration path does not enclose current carrying conductor, then the line integral, this line integral, will be equal to 0. It means that no current passes through this area enclosed by the given closed path. The general statement of Ampere's law considers the case when several long straight conductors pass through the surface bounded by the integration path. Here is the figure for this situation. So we have three currents, I1, I2, I3, and two of them are bounded by the integration path. So according to sine rule for currents, here I3 is positive, I2 is negative, and I1 is not enclosed by this integration path. How do we find the sign for the currents which are bounded by the integration path? The sine rule states, curl your fingers, the fingers of your right hand around the integration path in the direction of the integration. Then your thumb of your right hand indicate the positive current direction. So here in this picture, in this figure, I will curl the fingers of my right hand around the integration path, and the thumb of my right hand shows for the I3 into the screen, in the direction into the screen, and this shows us the positive direction for the current. And I2 is out of the screen. It means the negative sign for the current I2. And I1 is not bounded by this integration path. So the general statement of Ampere's law is the following. The line integral of the total magnetic field equals the magnetic constant mu0 times the algebraic sum of currents enclosed or linked by the integration path. For our picture, by the enclosed current, we will have the I2 with minus plus I3. That is all, because I1 is not enclosed by this integration path. So let us make the summary of our lecture. The general statement of Ampere's law. The line integral of the total magnetic field equals magnetic constant times the algebraic sum of the currents enclosed or linked by the integration path. So magnetic field of a solenoid is equal to the magnetic constant times number of turns per unit length of the solenoid and the current which flows through each turn of the solenoid. Magnetic flux is a quantity that characterizes a magnetic field passing through a particular surface area. The total magnetic flux through a closed surface is always zero. So it is symbolically written like this. It means that every magnetic field line that enters the surface also exits from it. And so the net flux through the surface is zero. That is the Gauss law for magnetic field. So if we, for the electric field, have the flux through the closed surface of the electric field is equal to the charge enclosed in a closed surface. And for the magnetic field, this flux, magnetic flux through a closed surface is equal to 0. The current carrying loop or any other body experiences a magnetic torque given by this equation. That is, magnetic torque experienced by any loop, current carrying loop in a magnetic field. When a magnetic dipole changes orientation in a magnetic field, the field does work on it. In an infinitesimal angular displacement d theta, the work is given by this expression. So the work done by the magnetic field is equal to the magnetic torque times the angle through which this loop is turned in the magnetic field. Potential energy for a magnetic dipole is equal to the negative of the scalar product of the magnetic dipole moment and the magnetic field. The work done by the magnetic field during displacement of the current loop is equal to the change of the magnetic flux. So in order to find the work done by the magnetic field on a current loop during its displacement in the magnetic field, we can find it through the change of the magnetic flux, which is multiplied to the current flowing through the loop in the magnetic field. The lecture is over. Thank you for your attention.